Well, good morning. So yesterday, when I was preparing the slides, I realized there is a mistake. If this has to be negative 25, and of course negative 50 should be lower. Well, that's an easy fix. And I even posted a slide yesterday. It says just for curious people, so anybody else can just ignore it. I was just using the lab 2 from PY105 to actually derive an equations, which we don't have to, but we could, to get the same number again. So this is a question to you, just a review of definitions. So let's see, I've never tried this version before with a chair, but should work. All we need is string. Instead of using an applet, we can use an actual physical object. And if I start moving my hand up and down, I can generate pulses traveling horizontally, which is perpendicular to the direction of the wave propagation, which is pictured on the left. And depending on actually how vigorously I move it, my waves may have a special shape or nothing at all, just be something chaotic. But if I want to try something like this, well, I would have to move the turns of this spring in this direction. Well, doesn't really work this way. So there is a better slinky, a better spring, which demonstrate this type of a wave. And if I'll make this to be the source of the wave, there's a pulse traveling away. If I make many pulses, I generate a wave. And depending on the situation at this end, again, we can generate different type of waves. And this end might be solid, fixed, or freely moved. In any situation, if you look at individual location inside this wave, the wave particles, these turns, they move horizontally, and the wave propagates horizontally. This is the model of this situation. And now you just have to say the name, right, for each of these two, which is transversal, which is longitudinal, and my expectation, which unfortunately so far has never worked, is that this would have been 100% correct situation when everybody would give the right answer. Let's check. Yes, I want to resend it. And survey says no. Still, some people don't want to have me perfect question. I don't know why. Just once, please. Anyway, we know these are just the names. A name is a part of a language. We need to know that language so we could communicate and understand each other. That's it. And we saw this slide yesterday, and it tells us how can we come up with a mathematical description of a wave traveling away. We call it a traveling wave. It travels from a source. And the idea is very simple. If it's an ideal wave and one-dimensional motion so far, the displacement from equilibrium travels with a speed equal to wavelength over period or just distance over time. And the displacement from equilibrium here and now is the same as it was this time before at the origin, at the location of a source. That's it. And now, if we know the equation which describes the displacement from equilibrium as a function of time at the origin, could have been sine, cosine, or anything else in general, the same equation we could use to describe the displacement at any x, and I have a better slide with equations. So this slide is to show a picture. This slide is to remind what we know from PY105 again. And this is a simple harmonic motion which we could use to generate the wave at the location of the source. And each particle on the wave will have exactly the same period, frequency, angular frequency. And these are the equations which describe this particular simple wave. We used to call this a phase, but this phase now has a very special combination of variables, and this is so-called wave equation. The function depends on what type of a source do we use. If we use a cosine generator, the whole wave can be described by cosine, but could have been a sine, or in general could have been any other additional constant inside it. And that's what the amplitude, the maximum displacement from equilibrium, angular frequency. And this combination, which comes from just the expression for time, some people call time delay, because the same displacement we observed this time before at the origin. And if the location here, distance traveled equals speed times time, time will be equal to this distance traveled over speed. And if we do some algebra, we get this ratio. This ratio has a name, a wave number. In general, for two-dimensional, three-dimensional waves, people call it wave vector. It has a direction in general. But for us, it is just a number, a wave number. It can be, this is a definition of a wave number, but using all other relationships, we could calculate it differently. The last expression is the most important because it relates the wave number and the wavelength. So if we know the wave number, we can calculate the wavelength. Well, and here we look at several profiles of the same wave traveling in space with time. So it's like several snapshots, but these snapshots taken over a quarter of a period. So the big initial time, initial instant. Then we close our eyes and in a quarter of a period open, and we can see that the whole wave shifted by a quarter of a wavelength, and then another quarter, and then another quarter, and then another quarter. So in one period, it travels one wavelength. And the equation we've derived for the wave, based on the fact that the wave was propagating to the right into the positive x direction, but of course we could flip, the situation, have a chair here. Well, actually, that wave was traveling to the left. So what would we have to do to describe that wave? We would have to change a minus to a plus. That's it. So same equations can describe two different waves. One travels in a positive x direction, another travels in a negative x direction. And again, the relationships which we can use to connect different variables. Well, this is the old-fashioned from simple harmonic motion, how angular frequency and period are related. This is the new one. Now, of course, we can influence how fast the wave travels. Most important waves for us, or at least for now, sound waves. And the sound wave travel around 300-ish meters per second. And that speed depends on temperature and other variables. We don't need to know that. This is just an example. For example, if you have two different gases and one gas has heavier molecules, so they will be more inertial and the sound will travel slower, that's it. But if we have a string or a spring stretched, in that case, the speed of the wave is related to the tension. The higher tension is, the faster particles interact and the faster wave travels. But again, the heavier it is, more inertial. This variable represents the mass of 1 meter of that string. We call it a linear density. By changing, well, if we have a fixed string, like a guitar string, we don't change its length, we don't change its mass, but we can change the tension. And by changing the tension force, we can change the speed of the wave traveling on that string. Well, question. This is basically, again, a review of PY105. We have a motion equation, a wave equation, written in a general form. That's a general equation, and a specific equation which describes a specific wave. And we need to extract some information from that equation to use it to answer this question or any other possible questions. So you have to pick, well, an equation. How would you use it and choose your answer? Well, and while you're doing that, I'm going to start analyzing the whole structure of this equation. So in general, a wave equation looks like this. There's a number which represents the amplitude, a trigonometric function which represents how the wave is generated at the source, and then an expression in general. Name of that expression is a phase. It has parts, components. And if we look at the specific equation and at the general equation, that number, which is right in front of the function, is supposed to represent the amplitude. So this comparison immediately tells us the amplitude of this wave is supposed to be equal to 0.9 centimeters, 9 millimeters, 0.009 of a meter. Now, if I look at the last part, this comparison tells me that the wave number k should be equal to 1.2. And this is the unit of it, 1 over a meter. For example, if we look again at the relationship between the wave number and wavelength, to measure wavelength, we use meters. By some reason, when people write a unit for K, they ignore radians, they just write 1 over a meter. But when they write a unit for angular frequency, they write a radians over a second. Well, and now, of course, the most important comparisons should be done. From that comparison, we should extract the information about is it about a period? Is it about a frequency? None of the above. It's about angular frequency. And there is one definitely wrong answer among these three which you saw on the screen. That is 5. That is a definitely wrong answer. Because angular frequency is equal to 5. If we look at this specific equation and this general equation and compare, you see, the variable is connected to this constant t time. So this comparison tells us omega is equal to 5. So if omega is equal to 5, the period just can't. Radians per second. But we can calculate the period, of course, now, because it is equal to 2 pi over omega, 2 pi over 5. 1.2 seconds, about, I think. So if we know the number, now we choose the right answer. You can ask any question at any time, of course. So what else can we calculate? Well, lots of things now. For example, so the amplitude is a known number, 0.09. So the angular frequency is 5. The wave vector number is 1.2. So the wavelength will be equal to 2 pi over k, 2 times pi over 1.2. That's going to be meters. The speed of the wave should be equal to wavelength over the period. Well, we know the period, yeah, 2 pi over omega, 1.2 seconds. And if we know the wavelength, we can calculate that's going to be meters per second. But we also have another type of speed. We know that every individual particle inside this wave oscillates. And if it oscillates, so it stops momentarily, then speeds up, reaches maximum speed, slows down, stops again. So there is a maximum speed for each individual particle. And for that, we have to use the amplitude. So the amplitude, we just have to keep track of units. We have to use international system of units, so we have to convert anything not that. So times 5, wherever it is. And I think I have numbers. One more. We know that 10 meters of this string has a specific weight. So that tells us how to calculate the linear density. It just has to be equal to the total mass over the length. So the mass has to be converted into kilograms, and the length is 10 meters. So that gives the linear density, 0.012 a kilogram over a meter. But now, because speed, which speed? People sometimes confuse, we have two. The speed of a wave, this one. is related to the force of tension in the string and the linear density of that string. That is how we can calculate tension. So this speed squared times density, wherever it is, newtons. So I do have all the answers, all the numbers, including the speed and the tension. You can see actually here, this statement tells us that those two speeds are very different. How fast does it propagate? How fast does the wave move? About 4 meters every second. But the maximum speed of a single oscillation is 4 centimeters per second. So confusing those two speeds might lead to a mistake. That's it. Those are different things. Well, a question. So let's say someone has measured something and gave it to us in this particular form. From a mathematical point of view, it is a graph. Yeah? So we need to figure out how to use it to extract some important information. What, for example, can we say immediately, right now? The amplitude. The amplitude, according to the definition, is the maximum displacement from the equilibrium. And where is the equilibrium here? Well, at the origin. Doesn't have to be, actually. The graph could have been shifted up or down. The span between one maximum and second maximum, this span of the graph should be equal to 2 amplitudes always, automatically. But in our situation, we can just see one amplitude immediately. That will be equal to 8 millimeters. So the first answer is definitely wrong. The last answer is definitely wrong either. So I'm going to give you 10 more seconds. I'm going to switch, see your answers. 1 Mississippi. 10. That's the question number 4, and the most popular answer is wrong. Bless you. I tricked you. Well, tricked in a way. The information is on the screen. Who said? Definitely not me. That those are centimeters, 20, 40, 60. Do you see anything here? Could have been time, even anything else. So you don't know what it is. If you don't know what it is, you don't know what the units, you don't know what it represents. It might represent, for example, how a displacement at a certain location changes in time. But also, it might represent a photograph of a wave at a certain instant. So there are 2 natural choices for this axis. And depending on the choice, it might be either a photograph or snapshot, or a graph, an actual mathematical graph of something changing in time. So the right answer so far is not enough information, and you should ask, what is the axis? And I will tell you, that's centimeters. And now, of course, only now, the answer 40 centimeters will be correct. But to arrive at that answer, in addition to this axis, we also need to know a definition of a wavelength. This is a wavelength. This is a wavelength. This is a wavelength. Of course, this is a wavelength. 40 centimeters. Well, we don't need to see the whole graph. Yeah. We know it's centimeters. We know the wavelength is equal to 40 centimeters or 0.4 of a meter. We know the amplitude is equal to 8 millimeters or 0.008 meters. That's what we know. What else do we know? We know the speed, 20 centimeters per second, and that has to be converted, 0.2 meters per second. We know it travels in a positive x direction. That's how velocity points. So, well, the equation to this is the snapshot at t equals 0. If you want to write the wave equation, we have to choose between a sine and cosine. Now, and the minus or plus, omega t, well, the amplitude, and again, in general, would have been plus or minus k times x. So we have to make 3 choices. 1, 2, 3. And of course, we have to use the, well, this is a photograph. We can immediately say that at t equals 0 and x equals 0, y equals a. So that immediately tells us it has to be a plus, it has to be a cosine. We see it. And because it travels to the right, we have to choose a minus. So the equation should be in this form: cosine omega t minus k times x. The rest has been done already. And we know the amplitude, that's a number. We know the wavelength, so we can calculate the wave number. We know the velocity, which is supposed to be equal to wavelength over a period. So that tells us how to calculate the period wavelength over v, or angular frequency 2 pi over t. That's it. So, yes?
In your equation, can you explain why it's minus k?
This is based on our original reasoning for this pulse. The pulse travels to the right. And here we use the fact that here, at this instant, the displacement is the same as it was before. How do we calculate before? We have to subtract the amount of time it's been traveling. So it automatically, and we just keep using this fact. Later, for all waves, if it travels to the right, that's supposed to be a minus. And if we change the direction of velocity, we have to change it to a plus. And that's it. Now, this is the summary for a single wave traveling linearly on a spring. Again, you can play with the applet, I would recommend. Now, what's the next step? Well, next step, we have to talk about more waves. Yeah, what's more than 1, 2, 3? Of course, start from 2. The only kind of tricky part is the experiments based on using sound waves, because that's much easier, using speakers, whistles. But it is really hard to imagine the actual sound waves. We cannot see air. So instead of imagining sound waves, we will be imagining the waves on the strings, on the rope, because it's easy. But mathematically, there is no difference, of course. Mathematically, the equations are the same. So everything we say about one type of a wave automatically is correct about another type of a wave, back and forth. Sound wave is invisible, but can be heard. When there is no sound at all, of course, the room is not vacuumed, we would die. The room has a certain fixed value, average air pressure. But when we start pushing on molecules, those molecules start pushing on neighboring molecules, etc., and that's how a sound wave propagates. It needs a medium. It cannot travel in vacuum. That's a mechanical wave. Light waves can't travel in vacuum. And for a simple sound wave, like anybody, what is it? If you don't know, that's C minus. I lied. I don't know either. I don't remember anymore. But this is a pure tone, pure harmonic tone. And for the pure harmonic tone, the pressure changes in time and in space, well, according to a sine or cosine. So this is a photograph of that wave which was propagating. Well, we may generate many different tones, a combination of waves. That's what speech is and music is. So they all overlap, they all interfere. That's why we need to figure out what's happening when two or more waves travel together. The mathematical idea is simple. Add them up. But remember, we are adding displacements. So we have to go back in time. Actually, the very first class, the very first lecture of PY105, what is a displacement? What is an official definition of this physical quantity? Displacement. Anybody? For some of you, it's been even a longer time ago. If you took PY105 last year, or 2 years, or 3 years ago, but still, you want to say something? No? But you held your... Anybody? Use your own words. Okay. What is a displacement?
Difference from your final point and your initial point, not taking into account like the path traveled.
It is one of the meanings of this word. That's what I should have done, and I will. I will include that slide from PY105. This word has several different meanings. One of these, it's an actual action of an object being displaced from one location to another location. It also is a distance between the initial and final point. No matter how it's been done, if we don't care, we say it's been displaced by this amount. But an official definition of a displacement, it is a vector which connects the initial location and the final location, which points from initial location to the final location. That's a vector. So right here, we are adding two vectors, or more accurately, two components of two vectors. Because the displacement, see, the displacement could be up, could be down, could be zero, and relative to our standard choice of positive y direction, this vector has a positive component, this vector has a negative component. And if we have two waves, each displacement may be a positive number, a negative number, or zero. And when we're adding those displacements together, we add in numbers, components, could be positive and positive, negative and negative, positive and negative, negative and positive, zero and whatever combination. And the result will give us the instantaneous displacement of that actual wave. Let's try to look at it. So again, this is an applet you can play with one traveling wave when it reflects one way or another, and we will talk about it a little bit later. But standard traveling wave looks like this. And this travels away, and what's going to happen if we have two? Well, we have to use again our imagination. We have to assume that these two waves actually travel on the same rope. We just space the pictures of those waves, otherwise we couldn't see it. But if we add them up together, they would represent the actual profile of a new wave. How would we find this profile? Well, for example, let's see if it's going to work today. I want to do black. So this is the equilibrium location for all parts of this wave. And right now, let's say here, the wave number one displaced by one square up. And at the same time, I need, again, the equilibrium. These black lines supposed to be put together. Right here, I have displacement y2, smaller in magnitude, directed down. And right here, or do you see, well, probably this. Oh yeah, this end. This end should represent the equilibrium. This arrow represents an actual displacement of these two, which was found by adding two arrows. So this is how it works. Now, how do I erase everything? Okay. It is not, of course, easy to see, but, well, the pink profile represents the actual wave, which we would observe if two waves, red and blue, would be traveling simultaneously on the same rope. And, well, we can make it move differently. We can make them move in opposite directions. The principle doesn't depend on that. We still have to add individual displacements, and whatever happens, happens. Here we have a representation of two special cases. Again, what you have to imagine that the red and the blue lines represent two waves on the same rope, on the same string. So they travel right now toward each other on the same string. The picture just spaces them up so we could see them. But the bottom picture, the last one, represents what we would see on that actual wave. So two pulses approaching each other. Of course, right now, the actual profile is literally just the sum of two profiles. But what's going to happen when they start overlapping, or we say interfering? This is a snapshot of an actual wave. For example, right here, we have y1, y2, which is 0, and that gives y, which is equal to y1. But let's say here we have y1, y2, and actual y is greater than any of those. They point both in the same direction. When two pulses point in the same direction, the resultant always has a larger value. That's what we call a constructive interference. Bless you. That's, of course, not always the case. What's going to happen if the pulses are initially opposite to each other? Well, they will try to kill each other. The actual displacement will be less than each individual one. And there's a very, 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 very special case when pulses have exactly the same magnitude, exactly the same shape, but opposite to each other. What's going to happen in this situation? In that case, for a fraction of a second, the wave just disappears. They completely cancel each other. Of course, geometrically, it should happen because we have vector up, exactly same magnitude down, and the actual displacement is 0. But of course, it doesn't stay in this shape forever. In a fraction of a second, it changes again. So what are we going to see in a fraction of a second? Well, again, two pulses traveling away. If we understand what is happening to pulses, we understand what's going to happen to the whole wave. Well, pictures, photographs from the applet, constructive interference, destructive interference. We have several special cases to discuss. Special case number 1, when interfering waves have different but very, very close frequencies, and situation like that has a name, beats. Situation number 2, when waves have exactly the same frequencies and everything else is the same except direction. In that case, we can generate those waves differently. First time we can use actually two different sources. Second time we can use one source, but the wave travels, reflects, and the original and reflected waves begin interfering. So we start from beads. And first, let's hear them. Again, we will be using experiments with sound, but pictures related to, well, similar to waves on a string. Actually, first, let's see if they actually tune up. Not very good. Okay, more or less. You probably cannot. If they have exactly the same frequencies, the wave which one source generates should excite the second one. That's what we call a resonance. Now, I want to alternate those frequencies, so I'm just adding an extra weight. better, the newer, cheaper. Every year the quality just drops. Let's I can try to hear anything. When they both simultaneously excite waves, we hear something like, well, that's the best I can do. And, well, the intensity, the loudness of the sound changes, and of course it's getting louder, then louder, and quieter. The time between two loud sounds, that's the period. And this period is different from the period of each individual tuning fork. So how can we figure out how the beat, frequency beat period related to the actual frequency of each individual source? Let's, which is which? This is this one. And let's go down. And actually, let's make it like 300. So turn down the amplitude, turn on the second one. $300. Well, actually, I want them to be equal to each other first. So 319. Okay. Too much. 312. 316. 17, 18, 19. So now, oops, they both generate sound with the same frequency. What's going to happen if I start changing frequency? See how loudness changes very slowly. And here I have frequency 318.4. This one's still 319. And I can change the difference, make it larger. And now the period decreases, the frequency of the beats increases. And it's actually not very complicated to prove the fact that the beat frequency is just equal to the difference between individual frequencies. This picture represents the physics of that. We have two waves with very, very similar frequencies. So if you look at these two graphs, you don't really see the difference until you look very, very closely. And you can see that sometimes at this instant, both pulses have the same orientation. They amplify each other. We call it constructive interference. And that's when the maximum of the loudness is achieved. But over time, because there's slight phase difference, over time, there happens a moment when they cancel each other out. Down, up, completely destructive interference. Ideally, without any reflection, we wouldn't hear anything at all. Momentarily, that would become completely quiet. And then it repeats itself. And from here to here, or from here to the next minimum of intensity, we have exactly one period, beat period. And you can see that this time for one period and this time for one beat period is very different. And the equation is very simple. You can play with the applet, and the beat frequency is just difference between actual frequencies. And we are done with beats. Now two sources, same sources, but now they have to provide identical waves. Well, same loudness, which means same maximum, same amplitude, same maximum intensity, same frequency, same medium, everything is the same, only they have to face each other like this. Two waves travel and interfere. What's going to happen? Let's see if I have it. All right. Done with this. Did I close it? Okay. These are beats. You can see how the amplitude of the actual wave, the third picture, changes in time. Goes to 0, then again. We almost cannot see any difference for two top waves, but if we add them up accurately, we get maximum of intensity, then minimum of intensity. This is a picture of an experiment. For now, you just have to look at the space between the sources. In actuality, of course, every speaker generates a wave which travels away in all directions. So waves interfere everywhere. But for now, if we only look at the one-dimensional interference in the space between the speakers, these black and white strips represent how intensity of the sound changes. So if I would place a microphone, not this one, this is not accurate enough, between the speakers, I could find a place where there would be no sound at all, never, because two waves would be always canceling each other out. But if I moved the microphone slightly to the left or to the right, the loudness would increase from nothing to, and then it dies again. And now you remember. But we have to have a mathematical description of that. And it does exist. One wave travels to the right, second wave travels to the left. Come on, come on, come on, come on. For the wave traveling to the right, we have an equation. For the wave traveling to the left, we have an equation. And we have to mathematically add them together. And what does mathematics tell us? Well, if you look up how to add two signs, you get an equation which tells us the result. This equation has two parts. One part doesn't depend on time at all. Second part doesn't depend on location at all. So for each fixed value of x, there is oscillating, well, wave particle. Somewhere, this value may be even equal to 0. Nothing there. But somewhere, this value will be equal to 1, and the oscillations happening with maximum possible amplitude. And of course, that's not the only possible situation. We have many functions. We can add a sine and sine, sine and cosine, cosine and sine, and we can subtract them. And of course, it looks excessive for a problem like that. There has to be a better way. And it is. It depends on our understanding of how interference works. And we start from the easiest point, middle point. What should be happening at the middle point, no matter what? So we have two waves traveling from sources which have exactly the same amplitude, exactly same phase. So when those waves meet in the middle, they will travel exactly the same distance, which means right here, they always, again, will be in phase. When one points up, second points up. When one points down, second points down. So, for example, when the first wave reaches maximum, the second wave also reaches maximum at this instant, at this point. So it means the actual wave will have the doubled displacement or intensity, and that will be happening always, no matter what frequency of the sound is used or how far the speakers from each other. Right in the middle, we will always observe maximum of intensity of that wave, whatever wave it is. Sound wave, maximum of intensity of the sound. The loudest sound will be in the middle. Could have been light wave, the brightest spot. Could have been technically a wave on a string. So it would be moving up and down with the maximum span, always in the middle. Well, but now we know what to do, because every wave has exactly the same structure. It looks like this. The actual wave, again, looks like a sine or a cosine. So it has a maximum of intensity in the middle, but it must have somewhere nothing. And then it should have another maximum and another nothing. Maximum, nothing. And if you remember, the actual equation has two parts. One, which doesn't depend on time. Second, which doesn't depend on position. So right here, right now, the intensity is zero, but it will be zero forever, always. There is nothing here, because individual wave number one and individual wave number two will be canceling out each other. But only here, and only here, and only here, somewhere between these points, the actual wave will move up and down, but with a relatively small span and larger. And the largest span, the amplitude of a wave, will be reached here, then here, then here. And if we use our ear or very accurate device, and that would have been sound, here we would listen to the loudest sound. And here, under ideal circumstances, we wouldn't hear anything at all. Well, so this type of wave has a name as standing wave. It's a composition of two traveling waves, but the result doesn't move. It's fixed between two sources, between two speakers, and only particles move only, well, in this example, vertically, up and down. And if we compare several snapshots of a traveling wave with several snapshots of a standing wave, we can see the difference. This wave literally travels. We saw this picture several slides ago. This wave, again, we saw this picture. Did we? No, we didn't. Let's see, whatever happens. Something like this, yeah. An actual string or an actual sound wave, see, it doesn't move. This point never moves, but this point moves. Of course, the displacement here sometimes is equal to zero. Sometimes, at a certain instant. But in general, it moves with the maximum possible span with the amplitude. Well, so the snapshots of several profiles of a standing wave And now I have to say something about the name for each specific location. So here we observe the maximum of intensity. We call it the antinode or just maximum. Here we experience nothing. We call it a node or minimum. That's it. Now we can answer this question. How many antinodes do you see? This is a photograph. We call it a pictorial representation of a longitudinal wave. The longitudinal wave doesn't look like this. This is a transverse wave. But the longitudinal sound wave would have extra density here, average density here, lower density here. This is a counting problem. One of my many attempts to get the finally 100% correct answers. I will grade it based on your answers on a twofold scale, just A and F. Question number 5. No? 6. This is something I should start investigating. An antinode represents the maximum intensity, the maximum displacement from equilibrium. So this is how I would do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, if you still have any doubts, ask yourself, why? Now we can move on. In my specific experiment, the frequency was close to 330. The speed of the sound is a little bit lower than 330 normally, but if, could have been 330 as well. Now we need to calculate the wavelength. The wavelength of this wave, is the distance between these two antinodes which are in phase, or distance between these two nodes. This is a wavelength. Yeah. This distance is a half of it. And let's say this distance is a quarter of it. So how do we calculate the wavelength? Well, speed equals wavelength times frequency, hence wavelength equals speed over frequency. And what number does it give us? 1 meter. That's just an example. And now, for example, we can calculate the distance between these speakers, right? So different people would have been doing differently. I always count quarters. For me, it's much easier than do anything else. So from the middle point, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 quarters. A quarter of a wavelength. So the total distance between these two speakers is a pure geometry now, no physics at all. So it has to be equal to 9 quarters times length of 1 quarter, and we have to multiply by 2 because we have 2 halves. And I believe that answer is 4.5. Pure geometry. Visualizing things is important. Now, there's another question which I am going to skip right now, but I will do it tomorrow. So technically, we are done with two identical sources. So what's left? A wave generated as a combination of a driven wave and a reflected wave. And we actually saw an example of such a wave. We can see it again. This one. That's what we call wave pressure. Sound exerts pressure, light exerts pressure. I just invented a new demonstration, a wave pressure. Although it's more like wave anti-pressure. The pressure would pull it away. So this is a standing wave, but I can generate on the same string a standing wave of a different profile. Well, I have some toys I forgot to show you. This one. This one represents a traveling transverse wave. But if you look at this, this represents a traveling longitudinal wave. Not for sale. I only have one. Now, this type of waves can be generated easily. You just need a string and a function generator or motor. And we can see that depending on different conditions, the profile has a different shape. This is a stable profile, more or less stable profile. Well, this is a good one. With 3 antinodes, 1, 2, 3. But 2 nodes in between. But if I start changing, let's say, tension, we don't see any fixed profile anymore. This is not a standing wave. So in order to generate a standing wave with a very stable profile like this one, variables must fit certain parameters. And this is our immediate goal. How can we figure out what frequency should we use to generate a standing wave on a string, or that's a pure tone, requires PhD. So every standing wave has those special points, the points where nothing's happening, nodes or minima, the points where the wave travels with maximum possible amplitude, antinodes or maxima. And if we talk about waves on a string or in pipes like this one, a pipe open on both ends, or a pipe like this with one end closed, one end open, we can hear sound changes depending on. That's how my head sound. And the reason the standing wave survives is because when the end is open, we should observe the maximum intensity at the open end, and when the end is closed, molecules get stick to this end, and we should observe nothing, minimum, or the node. And well, or 2 nodes. If we just, analyze all possible situations, those are only 3 cases possible. So what do we do? Well, first we can start from a pipe open on both ends. When the pipe is open on both ends, well, our equation should fit that condition, but there has to be a better way. And there is. Physics. You just have to understand that a standing wave, a stable standing wave in a pipe open on both ends, should observe antinodes on both ends. That's what makes it stable. Now, how can it happen? Well, we know any wave looks like this, always. Up and down, any wave looks like this. So there is one situation when we have two antinodes fit inside the pipe. There is another situation when we have two antinodes fit inside the pipe in such a way so each end has an antinode, a maximum of intensity. There is another situation when we have antinode and another antinode, and again we have a stable standing wave generated in this pipe. All we have to do now is squeeze this picture and fit inside the same pipe. And that requires imagination. So instead of drawing through different pipes with the wave which has same wavelength, we should draw three pictures with the same pipe with the waves having different wavelength. So this is a case number 1, case number 2, case number 3. For the case number 1, we have antinodes out of phase. So 1, 2, 3. Out of phase, up, down. And if it would have been a string, the photograph, the snapshot, could look like this. This is literally this part of this wave, this part. So if the length of this pipe equals L meters, this part of a wave includes 2 quarters. So the length of this pipe will be equal to 2 quarters or 1/2 of a wavelength. That's it. If the length is slightly longer or slightly shorter, this standing wave with this particular wavelength cannot survive in that particular pipe. Next picture. Well, next picture, we have an antinode and an antinode in phase. This is literally this part. And this part looks exactly like one full wavelength. Well, we should start counting them. This is the wavelength number 1, which can be fit. This is the wavelength number 2, which can be fit. But we want to write it differently. We want to write it in terms of halves. Now, next one. Up and again down. So we need to add one more half of a wavelength. It's kind of something like this. So now, inside the same pipe, in order to generate a stable standing wave, that stable standing wave should have such a wavelength so we could have fit 3/2 of it. So now we can make a conclusion. For any pipe which is open on both ends, only waves with fixed values of a wavelength can survive, and those waves are this one. This running number 1, 2, 3, 4, 5, 6, 7 basically represents how many half wavelengths we can fit. But normally we would solve it for the wavelength number n. And number n begins from 1, then 2, then 3, then 4. And when we increase the number n, we decrease the wavelength. And shorter wavelength means higher frequency, higher pitch. So n equals 1 represents the lowest frequency, the longest wavelength. And, well, this device is the pipe open on both ends. And I can generate standing waves with different frequencies, different wavelengths by just spinning it. Low, higher, higher, even higher. So all I have to do just, well, make the sound travel through at certain, well, frequency. So we would fit 1 half of a wavelength, or 2 halves, or 3, or 4 inside the same tube. The length is the same. And the name for the first possible standing wave is a fundamental, and also we call them modes or harmonics. So the lowest mode, the lowest harmonic is a fundamental mode, and then we have secondary, etc., etc. These are pictures. That's an equation. But normally people solve it eventually for the frequency, speed, and wavelength related. If we know wavelength, how actually? Well, this is how speed is equal to frequency times wavelength. And of course, no matter how fast or how slow I move it, it's the same air in the same room, which means they all have the same speed, but depending on the wavelength we generate inside, the frequency is different. And this is how we count those frequencies. Well, the fundamental, the lowest one, and then the next higher, next even higher. Human ear usually can hear only fundamental and maybe the next, usually. Well, next part, a pipe closed on one end. And even if it closed only on one end, the official name is closed pipe. Open pipe, closed. And now, of course, we have to repeat the reasoning, but with one important difference here. Never we can observe an empty node. Molecules get stuck, glued to this. They cannot move. So we can do mathematics, but of course there has to be a better way. And that better way is drawing pictures. So I'm going to do it a little bit faster. I have to see an antinode here and a node there, or we call them maximum and minimum. And the shortest part of a wave, which looks like this, is a quarter of it. So I can fit exactly 1/4 of the wavelength. That will give me the fundamental mode. Next step, same pipe, same length. I'm asking a question, how else can I generate a wave in such a way? So I would have an antinode on the open end, but a node on the closed one. Well, this location wouldn't work. That would give me 2 antinodes. So I have to move another quarter of a wavelength. That gives me a new profile, or something like this. And now this length should be equal to 3/4 of a wavelength. Then the next will be 5, the next will be 7, the next will be 9/4. So in general, for any such a pipe, when one end closed and one end open, inside this pipe we can generate a standing wave with only odd number of quarters of a wavelength. Well, this is how we usually write it. N times, well, this is the wavelength number n, but this is a quarter. But n is equal to 1 or 3 or 5 or 7. In mathematics, people also write it differently, so you may see something like this, 2m minus or plus 1. But now this number starts from 1, 2, 3, 4. This is how in mathematics we can write an expression for any odd number. M equals 1, 2 times 1 minus 1, 1. M equals 2, 2 times 2, 4 minus 1, 3. And because of this mathematical difference, even different people in physics count those modes differently. We could call them, again, first, second, third. Don't do that. I don't like it. For me, and for many other people, it's much clearer to say that a pipe like that doesn't have even modes. There is no mode number 2. There is no mode number 4. It only has odd modes. First, third, fifth, seventh. So this is an equation which we should use when we need to relate the length of this pipe and the wavelength of a standing wave which we can generate in it. And of course, because speed is equal to frequency times wavelength, and the speed is the same, we can solve this equation for frequencies, speed divided by the wavelength. And this will give us a set of possible frequencies. The lowest one when n equals 1. The next one, which is not second, but third, when n equals 3. The next one, which is fifth, etc., etc. And these are nice pictorial representation of those standing waves which could be generated in a closed pipe. You can see we just count quarters. 1 quarter of a wavelength, 1, 2, 3, 3 quarters of a wavelength. String. Well, we saw an example. And that example is very, very simple. If these two ends cannot move, those two ends are nodes. Which automatically tells us what to do. The first profile would look like this. Well, again, we should keep in mind how any wave looks like, something like this. If the length of this string is L, this is not a length, this is not a wavelength, this is a half of it. L equals 1/2 of a wavelength. But the next would look like this. L equals 2/2 of the wavelength. That's the wavelength number 1, that's the wavelength number 2. So we can see that, again, the equation for any wavelength of a standing wave generated on a string with both ends fixed is exactly the same as the equation for standing waves generated in a pipe with both ends open. So they are mathematically identical. These are several pictures, and this is the conclusion. Mathematically identical. There is no difference. So if you have a string, something like this, fixed ends, and if you have this called a bluegill, if you have a bluegill, mathematics is exactly the same. What is the difference? Well, how do we calculate or measure speed? For the bluegill, the speed represents the speed of sound in this room. For a string, speed v represents the speed on a string, square root of tension over linear density. So pictures. Several, again, pictures for a string, and we're done with general theory of standing waves in any situation. This is the summary: string or a pipe or a tube with both ends open, a pipe or a tube with one end open, one end closed, pictorial representations, equations, everything. All right. I will do this demonstration tomorrow, but I will solve this problem now. First of all, every time we have to first make a statement. What kind of a pipe is it, if we have a pipe? Is it a pipe with both ends open, or a pipe with one end open and one end closed? We look at this picture. This tube has opening at the top, and here we have water closed. So this is not this case. This is this case. Check. For this case, what do we know? Well, we know how to relate the length and wavelength. We just need to remember two things about a pipe like that. We have to count quarters, and the number n must be odd, like we are. That's it. Now, tuning fork generates a sound with a specific wavelength. Specific frequency, specific speed. Speed is given by the environment, and that's what I think what we're looking for. And we are generating several waves. First time, we can hear a loud sound when the water level is 20 centimeters. I make it horizontal. It's easier for me to draw 20 centimeters. So at first time, the water level is here. And second time, we hear the loud sound when the water level is 70 centimeters away from the top. Now we know it has to be antinode, node, antinode, another node, which means we have two nodes, which is a half of a wavelength. Well, tomorrow I'm going to do more. Thank you. But now you're supposed to be ready for the lab, which is in 130, room 130.